let us discuss advancements in current mirrors. In order to suppress the effect of channel length modulation, a cascode current mirror circuit is used. The current mirror shown in Figure 1 incorporates the cascode technique. This approach effectively reduces ratio errors caused by discrepancies between the output and input voltages. By applying this technique, the performance of the current mirror is significantly improved. Figure 2 represents the small signal model for the cascode current mirror shown in Figure 1. To calculate the small signal output resistance, we set the input current II to 0, which causes the small signal voltages V to become 0. This transforms the circuit into an equivalent form. In a cascode current mirror, two transistors are stacked in a specific manner. A common emitter transistor, or common source in MOSFET, is placed above a current mirroring transistor. The combination of these transistors forms a cascoding structure, where one transistor is used to shield the other from variations in voltage. Improved output impedance. The output impedance of the cascode current mirror is higher than that of a simple current mirror because the cascode transistor helps to isolate the output transistor from voltage variations at the output. This results in better current regulation and stability. Better performance. The cascode current mirror increases the output resistance and reduces the voltage drop, leading to better current copying precision and reduced error due to variations in load voltage. This makes the cascode current mirror particularly useful in high-precision applications where accurate current replication is required. Increased voltage headroom. By adding the cascode transistor, the voltage drop across the output transistor is reduced, meaning a smaller voltage difference is required to maintain the current mirror's functionality. This results in improved voltage headroom, which is beneficial in low-voltage designs. Let's look at the transistor configuration in a basic cascode current mirror. This circuit utilizes three main transistors to achieve its functionality. First, we have M1, the reference transistor. Its role is critical as it sets the reference current, which depends on its gate-to-source voltage or VGS. Essentially, M1 determines the base or benchmark current for the entire circuit. Next is M to the output transistor. This transistor is responsible for mirroring the current set by M1. It ensures that the output current matches the reference current, making it the core component for the current mirroring functionality. Finally, we introduce M3, the cascode transistor. This transistor is placed strategically between M2 and the output. Its primary job is to improve the overall performance of the circuit by increasing the output impedance. It achieves this by isolating M2 from voltage variations at the output. This also enhances current regulation and ensures stability, making the circuit more robust. Together, these three transistors work in tandem to provide precise current mirroring while addressing issues such as output impedance and voltage variation. This configuration is particularly useful in applications requiring high precision and stability in current replication. Now, let's look at the transistor configuration in a basic cascode current mirror. This circuit utilizes three main transistors to achieve its functionality. First, we have M1, the reference transistor. Its role is critical as it sets the reference current, which depends on its gate-to-source voltage or VGS. Essentially, M1 determines the base or benchmark current for the entire circuit. Next is M to the output transistor. This transistor is responsible for mirroring the current set by M1. It ensures that the output current matches the reference current, making it the core component for the current mirroring functionality. Finally, we introduce M3, the cascode transistor. This transistor is placed strategically between M2 and the output. Its primary job is to improve the overall performance of the circuit by increasing the output impedance. It achieves this by isolating M2 from voltage variations at the output. This also enhances current regulation and ensures stability, making the circuit more robust. Together, these three transistors work in tandem to provide precise current mirroring while addressing issues such as output impedance and voltage variation. This configuration is particularly useful in applications requiring high precision and stability in current replication. Let's discuss voltage control in the context of a cascode current mirror. In a traditional current mirror, one of the key issues is that variations in the output voltage can introduce errors in the mirrored current. This happens because the drain current in the transistors depends on the voltage across them. Even small changes in the output voltage can disrupt the accuracy of current mirroring. The cascode configuration addresses this issue effectively. The additional transistor, M3, acts as a buffer for the output voltage. By isolating the output transistor from these voltage variations, M3 helps stabilize the drain current. This significantly reduces the errors caused by fluctuations in the output voltage, ensuring better current mirroring accuracy and reliability. In summary, this voltage control capability makes the cascode current mirror highly precise and ideal for applications requiring minimal current variation under changing conditions. Let's now discuss the concept of output impedance in a cascode current mirror. In a simple current mirror, the output impedance is limited, which means that changes in the output voltage can significantly affect the mirrored current. This can result in less accurate and less stable current mirroring. By introducing the cascode transistor M3, the output impedance of the current mirror is significantly increased. This higher impedance helps to minimize the impact of output voltage variations on the mirrored current, making it much more stable and precise. This improvement in output impedance is especially critical for applications that demand high accuracy and stability, such as precision analog circuits or sensitive measurement systems. In summary, the addition of the cascode transistor enhances the output impedance, ensuring a more accurate and reliable current source in the circuit. The cascode current mirror offers several key advantages over traditional current mirrors. One of the main benefits is higher output impedance, which directly improves the current regulation. A higher output impedance reduces the impact of voltage fluctuations, keeping the mirrored current more stable. Another advantage is improved current matching. The cascode configuration minimizes the current mismatches that can occur due to variations in the circuit components, resulting in more precise current mirroring. Finally, the cascode current mirror has a reduced voltage drop thanks to the cascode transistor, which improves the efficiency of the circuit and allows it to operate with better voltage headroom, making it suitable for low voltage designs. The Wilson current mirror is a circuit that accepts an input current and produces a precise mirrored current at its output terminal. It consists of 3 transistors and is named after George R. Wilson, who created this configuration in 1967. This mirror is frequently used as a current source when a constant bias current is applied to the input terminal. In CMOS circuits, the Wilson current mirror is typically implemented using 4 transistors. For accurate operation, transistors M1, M2, and M3, M4 must be well matched. When the input and output potentials are nearly equal, the currents are mirrored with high precision. However, mismatches due to variations in lithographic processes and threshold voltages can cause discrepancies. The mismatch in current between the input and output can be described mathematically by the formula shown here. The drain current depends on the device size and the difference between the gate source voltage and the threshold voltage. By expanding the formula in a Taylor series, we can express the mismatch in terms of threshold voltage and geometrical variations. Threshold voltage variation is a key factor influencing the current mismatch in the Wilson current mirror. Studies have shown that the standard deviation of threshold voltage variation ranges from 1 to 3 millivolts. By biasing the transistors with a gate source voltage exceeding the threshold by several tenths of a volt, we can minimize this error and also reduce the current noise from the mirror transistors. Geometrical mismatch between transistors is another source of current error. To minimize these effects, careful layout is essential. One strategy is to subdivide transistors M1 and M2 into parallel devices, arranged in a common-centric or interdigitated layout. This helps ensure that both transistors experience similar operating conditions, reducing mismatches. The output impedance of the Wilson current mirror is much higher than that of the standard 2-transistor current mirror. If there is no body effect in M4, the output impedance is given by the equation shown here. However, in the case where all 4 transistors share a common body connection, the output impedance increases slightly, as shown in the second equation. One of the main limitations of the Wilson current mirror is its high minimum voltage requirements for proper operation. The minimum voltage between the input node and ground is typically around 2 volts, and the total voltage to ground often exceeds 3 volts. These high voltage requirements make the Wilson current mirror unsuitable for low-voltage circuits, where newer designs with low supply voltages are often preferred. Current mirrors are versatile components in analog circuits, playing essential roles in a wide range of applications. In this section, we will explore 4 key applications: biasing circuits, current sources, differential amplifiers, and cascode amplifiers. By maintaining stable and precise current levels, current mirrors help optimize the performance of these circuits. One of the primary uses of current mirrors is in biasing circuits. They are used to provide a stable and well-defined bias current, which is essential for the proper functioning of other components such as amplifiers and differential pairs. By mirroring a reference current, the current mirror ensures that the biasing conditions are consistent, which helps maintain the operating point of the circuit. Current mirrors are also employed as current sources in various circuits. By mirroring a known reference current, they generate a stable output current. This is particularly crucial in applications where a constant current is required, such as in current steering digital to analog converters, DACs, or voltage regulators. The precise control over current ensures the reliability of these systems. In differential amplifier configurations, current mirrors play a vital role in maintaining balanced operation. They provide mirrored currents to the input differential pairs, which helps improve common mode rejection and ensures symmetrical signal handling. This results in enhanced performance, making differential amplifiers an essential part of operational amplifiers and communication systems. In cascode amplifiers, which combine a common emitter stage with a common base stage, current mirrors help maintain a consistent bias current for both stages. This contributes to the overall improvement of the amplifier's performance, especially in applications requiring high gain and wide bandwidth, such as in radio frequency, RF, circuits. Thanks.